We are all excited looking at change, and we want to believe that these changes start to happen at the nanoscale, right? We are strictly reductionists, all of us here, I would think, and that things start from small and then expand into to explain what we see in the macro scale. But we are also, I'm pretty confident this audience is really, including myself, observational freaks, right? We like to observe, we like to see. And one person who articulated this pretty nicely is Gerd Benning. I'm sure all of you know him. He is one of the co-inventor of the AFM. And several prizes, including the Nobel Prize. In one of his speeches, he kind of said this statement that I like. Once you can observe something, you're usually in a position to change or modify it. A laser, for example, can measure a surface, but turn up the power and you destroy it. The same is true of AFM. In principle, this is something we thought about from the very beginning. So it's interesting that he put AFM and laser together. That's really SNOME, which really allows us to observe not just topographic changes, but also chemical changes in real time. And really that NeaSCOPE gives us this superpower, super ability to look at things in that scale. So I'm going to tell you about such changes in two kinds of materials, on phosphorus allotropes and transition metal dichalcogenides, and a particular kind of TMDC, which is an in-plane heterostructure. So to begin with this phosphorus, so how many of you knew that black phosphorus was invented 1 hour flight from here, from Hamburg? So this is quite appropriate, right, to talk about black phosphorus here. This is the inventor's painting, Henning Brandt, and that thing that you see, not sure if I have a pointer here. Oh yeah. So that thing here is black phosphorus, an exaggerated view of black phosphorus glowing. And it's very reactive material due to the, when you have a phosphorus material, for example, black phosphorus, all the phosphorus atoms have these lone pairs. So, these free electrons to interact. And as a result, it's extremely reactive. And those of you who worked in this material know that as soon as you put it under your SNOME, it's in the beginning, it's okay, it looks nice, and then literally a few minutes later starts to form bubbles, and these bubbles start to grow and connect, and then you have a different material in effect pretty soon. So if you sit in one of these bubbles that you see here in the image, if you sit in one of these points and take spectra, you see something like this. So in the beginning, the spectra is sort of flat, and then as time goes on, it starts to have structure, and eventually you get something like this. So this is really quite exciting, right? You can observe really in front of you bonds making and breaking is what you're looking at. And this band, this range, is known to be phosphorus oxide and phosphoric acid species, and you can they have this vibrational response that you can map, and that's what you see here. And so it's quite broad, the spectra. There's so many overlapping modes that exist in this range, but it's pretty much something with phosphorus and oxygen stretch modes. And so you can tentatively assign them as PO single bond stretch mode and PO double bond, as well as this symmetric phosphate mode that you see. So oxygen plays a major role. That's the take-home message. The reaction rate is determined by how much water and oxygen you have around this material, and it's quite complex. But you understand that water and oxygen is important for this material to fall apart. And so, so then you do something about it, and that is you passivate this, and my group and others have worked on this. And what we found is if you have a double layer coating, you can passivate it for quite a while. So recently, instead of working with this one material that is quite reactive, we started looking for a newer allotrope of phosphorus, and we have found that violet phosphorus, the other allotrope of phosphorus material, is quite stable, much more stable. Of course, when you work with phosphorus, that's the first thing you do. Is it stable? That's kind of the important question. And this is, in fact, we did the first experiment on this material, and we found it, depending on what substrate you use, it can be extremely, actually quite stable without having to coat it, at least for a while. And it has a very complicated crystal structure. Black phosphorus has this monoclinic, orthorhombic crystal structure, whereas violet phosphorus is monoclinic, but it's complicated. You have these phosphorus tubes that connect with each other and form a very difficult, a very complex structure. Much of these Raman spectra that you see below here are not yet assigned. But we think that that structure has something to do with the fact that it is more stable. If you measure with SNOM again over time, what you find is actually quite stable. So if you try to measure the thickness change over time and draw a line, the slope of the line is about 9 times steeper in black phosphorus compared to violet phosphorus. So it's, time is the x-axis here. It degrades much slower and also differently in the way it looks, how it degrades. If you now do the same kind of spectroscopy on these bubbles and compare the two, and literally superimpose what your assignment for black phosphorus on violet phosphorus, what you notice is something interesting. You see that the spectra is it's narrower in violet phosphorus compared to black phosphorus, and that comes from this PO stretch mode missing, a certain portion of it missing here. And so in both cases, oxygen is important to degrade the material, but it's the strong PO stretch mode in BP, which is not observed in VP, suggests reduced oxygen insertion, and we have tried to understand this recently by trying to look at the structure and oxygen diffusion through the material due to the structure of violet phosphorus being different from black phosphorus as a contributing effect on this. So I'm going to move on into the next one due to time, which is another very exciting material in transition metal dichalcogenide. It's a heterostructure, two materials stitched together covalently in plane, and it's a monolayer. So this work allowed us to use sort of an upcoming technique that neaSCOPE is putting out at the moment. So I'm going to tell you sort of a correlative imaging of the degradation of this material. So the monolayer looks like this. If you look at it with optical microscope, what you notice is the color of the outer layer is different from the inner layer because the two are different materials. The outside is WS2, the inside of this material is MOS2, and the two are covalently linked at this interface. And that interface is turned out to be very important. It's an alloyed interface. It has both materials in it, and it's about 100 nanometer in width. So it contributes both from the oxidation or degradation point of view of this material, as well as its optical properties. It plays a major role in that. And the nice thing about this material is if you take a far-field PL spectra near the band gap of WS2 and MOS2, the two are nicely separated. So this is the peak for WS2, a known PL peak, and MOS2 somewhere here. And at the interface, you have somewhat in between peak. And the Raman modes as well are quite separated. So it's nice from a hyperspectral imaging point of view when you try to look at both of these materials in one go. So what's important is if you look with TEM of this material, what you find is both the inside and the outside of this material are heavily, the outside is heavily or dominantly tungsten made, tungsten disulfide, and the inside is molybdenum rich. Whereas the interface, which is the middle panel here, is quite mixed. So you can see the atoms from both of these materials, tungsten as well as molybdenum. So it's quite alloyed material. And as I said, this is quite important for what I'm going to tell you. So NASPEC put this spectrometer, you know, in addition to the photodiode detector for single frequency imaging, and that turned out to be already, I mean, still work in progress, but it's already very powerful. And so I'm going to try to tell you some things that we did using this setup. So, here is the sample, so we started by take a hyperspectral image at each pixel on this sample and form this 3D cube of the PL emission. And so this XY plane is the sample plane, and the Z-axis is the energy axis. This is similar to hyperspectral in nano-FTIR, those of you who work in nano-FTIR. And so we follow this cube over time, so how it changes over time. And as you can see, it's quite hard to understand. And the cube changes, so the way to understand this is to this is how we do the measurement. Someone asks, we can go talk about this, but this is the data I want to focus on. So now if you take a section cut of this cube at the 1.4 EV and 1.81 EV, which are near the band gap of WS2 and MOS2 respectively. These are the neutral exciton emission. You notice something like this. So over time, so this is just a section cut of the top panel here at these two energies. So you notice that the PL on WS2 changes. So start to concentrate on the edges and then eventually disappears. Whereas in the MOS2, it changes, but not dramatically like WS2. So when I first saw this, I was like, wow, this is cool, right? Something is going on. And you can also look at the interface by subtraction of signal. You can isolate the interface region as well, which is a 100 nanometer thick in PL emission, which is quite nice. So now I'm going to tell you a story that explains this data, and this is the best story we came up with. So so the story goes like this. So this 2D material, it's known that they are sulfur vacancy rich on the outer layers, particularly those that are made with CVD. Those of you who work with CVD samples know this. They are the sulfur vacancies are rich on the outer layer. And so, and they are a thermodynamically stable region for oxygen substitution. So oxygen is easy, finds it easy energetically to substitute at those vacancy regions, and it works itself inwards, oxidizing the material. So that's why it starts out from the outer edge of this material and starts to degrade. So, but then it concentrates, the PL concentrates on the edges. So there is a reason for that. I will tell you in a little bit. But then as it comes closer to the MOS2, it stopped. This propagation of oxidation is stopped by the interface. And the reason is that interface is alloyed region. And the alloy means that it is also thermodynamically stable region. And as a result, oxygen substitution becomes less prominent in those regions. And also strain is different there. Due to strain, it's also at lower energy. And for those reasons, the oxygen substitution is reduced. And as a result, it protects the inside MOS2. So this is how we could explain these results. And I'm going to show you, the rest of the things I'm going to show you is basically enhances or really elaborates on this story. So this would be false if, for example, WS2 degrades faster than MOS2, right? That would explain this data. So what we did is we took this MOS2 and WS2 similarly prepared CVD samples and did similar experiments over time. And what we found is, yes, there is some difference between the two, but it does not explain this dramatic difference over time that we saw. So the reason is not because one degrades faster than the other. And now, one thing we know is, so, as I said, this sample helped us to sort of use this correlative imaging, near field with tip-enhanced PL, tip-enhanced Raman, as well as optical imaging and AFM, all in one, right? So that's, this is nice. So if you look at it with optical microscope, the sample that we did the experiment on is circled there. If you compare this sample with the one that we did not look at, given the same ambient condition, the sample, the whole flake, the whole sample is exposed to the same condition for many days. But the difference that you see between this and that, even just with optical microscope, comes from the fact that that particular sample is exposed to laser. So what you saw is photodegradation, clearly. Because now if you look also with fluorescence imaging, which you could do with the same setup, what you notice is for WS2, the outer layer is completely quenched, whereas the flakes that are not exposed to light are still glowing. So you can clearly say that the reason for the degradation is photo-induced. So this is important. The other thing you can say is because you have this correlative imaging, you can now look at the topography as well as the optical image with second harmonic near-field image using visible light. We use 632 nanometer. So what you notice is something very interesting. First, the topography change can be measured, and what happens is the topography in the middle has grown more than the outer, which shows, the outer layer has larger topography at the end than the inner layer, which shows degradation. This is also known. But the other thing is the dielectric function, which, as Rainer talked about, the real part of the the dielectric function is directly related to the amplitude, as you all know. And so what you see is an amplitude image of the flake before experiment and after the outer layer has completely degraded here. So if you compare in the beginning, both of them have the same contrast, amplitude contrast, which means very similar dielectric constant at 632 nanometer. And this is true. These are measured for monolayers of these materials. So you see the same contrast, so near field correctly picks that. But at the end of the day, after several days, when WS2 has degraded, you can see that the outer layer is almost similar to the substrate, which is SiO2. It's completely oxidized. So you can measure that number as well in this way. The other thing you could do is you can also take Raman, tip-enhanced Raman, and also compare structural information with the PL emission with this technique. So we did that, and the result, as you can expect, is similar to that of the PL. Wherever you have more WS2, you have more emission. So it kind of correlates with our PL measurement. And again, the inside is, over time, still there, MOS2 is still there compared to the outside. Okay, let me run a little bit faster. Now, this is the only thing we did not do with SNOM, with this correlative imaging, which is to use electron emission. Because the alloy, as you can imagine, is very important, right? if the story I told you is true. And so we try to go ahead and explore the effect of the alloy for electron. If you raster scan with electron beam, what happens with highly alloyed, or the intermixing is high compared to the one that's not alloyed. Turns out in both cases you can form these holes. The holes form as you raster scan electron beam on the sample, but the increase of the hole, the size of the hole increase over time for the alloyed region is much less compared to the unalloyed region, the pristine region. And you can do that at different temperatures, and you can see that the thermal property of the sample can be enhanced by alloying the sample. So the story goes on and on. I mean, you can imagine that data cube I showed you can take you a lifetime. I mean, there's a lot of information there because you have two materials, there is an alloyed interface, and both of these materials have different exciton species. I only talked about the neutral excitons. And so you can follow all of them, what they do over time. Strain plays a major role. For example, what happens is the spectra shifts as the material degrades to a higher energy as it degrades, because strain is relaxed, and as a result, you see this significant, by 10 nanometer shift to the blue as the material degrades. And also the edge regions are highly alloyed, highly strained. As a result, they act as a kind of sink for excitons. So the excitons like to be there. And since it's alloyed, it's more stable, so you see enhanced stability there. So a lot of information there, but I want to just tell you one last thing, because my Mike is standing there. So this is the coolest thing I should have been talking about, but we are now trying to do with NeaSCOPE. That's the beauty of working with NeaSCOPE, is they're more like collaborators to me than they're open to new ideas. And so trying to do this with tapping mode AFM as opposed to simply doing hyperspectral with a CCD. Can you do a similar thing you do with a regular SNOM scattering type for inelastic scattering by using tapping mode? This is the first data. We have had this data for a couple of years now. We haven't written anything yet, but it has the potential that it is possible. It's not as sensitive as elastic scattering, but we did initial measurements. So this is using, do I have a minute or?
Basically, no.
No, okay. All right, so in any case, it started to work, and I think there is more development on this from NeaSCOPE, and I'm so excited to see that coming up. All right, so in the end, the most important slide, lots of collaborators and students, postdocs who worked with me on the things I've told you, and support from NSF and the Air Force. And thank you so much for your attention.